All right, so this is an application of complex numbers, right? So the question always comes up, what do you use these things for? So here's something that's a really specific application. It's a pretty interesting application. So when you talk about the impedance, what's it mean? Let's just think about the word impedance for a second. What does it mean to impede something? To get in the way. So if you're impeding someone's progress, you're kind of halting their progress or slowing their progress, for example, right? Does that make sense? Yeah. So impedance in a circuit has to do with what are the things that cause the current, the signal that's traveling through the circuit via the current. What causes it difficulties in getting around the circuit? What causes it to slow down, for example, right? Gets in the way of the current passing through the signal. And so we call that impedance. And it's a number when we want to talk about impedance in electronics. Now this is more specifically in an AC circuit too. So this is stuff you probably haven't talked about necessarily. I don't know if you have or not in science. But what's the difference between an AC circuit and an DC circuit?
I know.
What is it?
Alternating current and direct current.
Okay, so AC stands for alternating current and DC stands for direct current. So for example, if you plug in, okay, this is where you guys really can't be talking about, okay? So when you plug in one of those little blocks into the wall, it's like a little rectangular thing, and then there's a little skinny cord that goes up to whatever you're using. Usually what that is, that's a transformer that's gonna take the alternating current. When you plug something into the wall, line voltage is alternating current, right? So it's always, it wiggles around very fast. It's 120 hertz, so it goes 120 times a second. It's going to oscillate back and forth, and it's just changing the polarity, changing from positive to negative, and positive to negative. And there are some complicated reasons that we do that with electronics, but that's what line voltage is. And so if you need to turn it into a direct current is one which does not alternate. It's just a steady direct current that's flowing through a circuit. Then you have to have, usually we have those little blocks, you know what I'm talking about. Usually they're black colored blocks, you stick it in the wall, and then it goes through that little transformer, and then it sends the direct current signal to the appliance, whatever it is. When you're talking about a circuit that's using alternating current, an AC circuit, that's where we use this complex impedance like this. Okay, we treat direct current circuits a little differently, but no, you don't need to. You don't need to write this down. This is just kind of interesting, and it's not. You'll learn about this if you study electrical engineering or physics. You'll learn a little bit about this. Like if you take physics in college, there will be a part of your electricity and magnetism course where you'll learn how to do some electronic stuff, analog electronics. Okay, it's good stuff. So when you split it up this way and you think of impedance as being this complex number, well, we recognize that there's a real part and an imaginary part. So the real part, if we write it this way, Z equals X plus YI. X is the real part of the impedance, and that's what we call the resistance. Okay, that's regular old resistance, like we talked about in a toaster the other day or something, right? Or in a light bulb, where the current that's passing through the resistor, it's being dissipated as heat, and it makes it hard to push the current through the resistor. It's being resisted, right? And you lose some energy then as heat as you pass current through the circuit. That's the real part of the impedance. Now the complex part is a little different. The complex part is what we call reactance, and you don't lose, it dissipates no power, but that's where the current is passing through these other components. It's passing through the inductors and the capacitors, and some things happen to slow the current down, like it gets sloshed around, and in this inductor it tends to kind of flow back and forth, and the harder you push the current through, the stronger the magnetic field is going to tend to try to resist that, create this backwards current that's going to slosh against it. And in the capacitor, it kind of gets stored on the walls of the two plates of the capacitor, and the field transmits some energy through that gap, but you don't lose anything, okay? But it still does impede the flow of the current. So they both play their parts, and it's kind of complicated. There's a lot more to it than what I'm saying. Typically the reactance is going to be out of phase, the signal is out of phase with the real part, with the resistance, and that's all stuff you'll learn about when you study this in college, if this is something you're interested in. But let's just look at some really simple examples. Let's look at a really simple example here of a very simple circuit that has these three components in it. Let's say it has a resistor, an inductor, and a capacitor, one of each of the three kinds of analog components that we put in a circuit. And let's say that oh, and by the way, the unit for impedance is always an ohm. It looks like a horseshoe. It's an omega, capital omega, Greek omega is what that letter is. And it's measured in ohms. OHM would be how we'd spell, there it is, ohms. And that's the unit of resistance, by the way. If you measure the resistance of something, it's measured in ohms. But when you're calculating the impedance that's generated by these other components, it also has the same units because it does the same thing. It tends to resist the flow of electricity through that circuit. So what if we had a 3 ohm resistor and a 5 ohm inductor, these are the impedances, and a 6 ohm capacitor? How could you add those up and get the complex impedance? Here's the recipe for doing that. Whatever the impedance is of the resistor, well, the complex number that goes with that is just 3. It's always going to be completely real. The inductor, whatever the impedance is, the complex impedance is going to be that value times I. Okay, so it's going to be imaginary. And then for the capacitor, whatever the impedance of the capacitor is, it's going to be the opposite of that value times I. So if the capacitor has an impedance of 6 ohms, then its complex impedance is negative 6I. Okay? And so if we wanted to, for example, like let's just take some circuits, very simple circuits. We call these series circuits. And this is something you guys probably, I know you've talked about. What's the difference between a series and a parallel circuit? Okay, so there's one thing, Jake. Remind us about that. With series, what's something that's true?
A series, the switch will shut off everything, but parallel,
Okay, good. So a series, and there's a way, the word actually tells us a lot. When we've got components that are connected in a series circuit, they're always connected in series, meaning they're the one after the other, right? So in this case, we have a resistor followed by an inductor followed by a capacitor, but there's only one path that all the electrons follow, right? When we pass the current through the circuit. Same thing here. Oh, by the way, that little symbol right there, that just stands for a source of electricity. Yeah, that's all that is. So there's some current that's flowing in this direction, coming back in that direction, let's say. Okay. Same thing here. We've got slightly different values for each of the components. But here's another example of a series circuit. Here's another one. This one's actually got 2 resistors in it, so it's got 4 total components. It's really easy to find out what the complex impedance of a circuit is. How do you think we're going to find this one? What do you think we do? Well, what's your intuition tell you? That the total impedance is just the total amount that you just add them up, don't you? You just add them up. Because it's going to be the total contribution of the impedances of each of the little elements that we're pushing the current through, right? So this is really simple. All we're going to do here is just add all those things up. Piece of cake. So the total impedance in this case is going to be 2. And then for an inductor, remember that was just going to be whatever that number is times I. So it's 2 plus 5I. And for a capacitor, remember it was the impedance times negative I. So it's going to be minus 7I. So what's the total impedance for that circuit? 2 minus 2I. There you go. Right? No big deal. Let's just do one more. Like, what would this one be over here? So negative 2I plus just plain 8, because that's the resistor, minus 6I, because that's capacitor, and plus 4I. And then so we add all these things up and we get 8. What's that going to give me? Minus 4I. Everybody agree? Okay. So that's good. I mean, it's telling us in this case that the resistance is 2 and the reactance is -2. But maybe all we want to know is which one is harder to push current through. We want to know just what's the overall, if I want to think of just an overall impedance, how hard is it going to be to push current through this circuit compared to this one? Which one do you think has more impedance? Well, we don't really know based on this. Any idea how we could maybe find out? Any suggestions? I'm just going to step back a little bit in our conversation of Friday. Wow, what do you think about, what do you think? If I just want to come up with what do you think? What do you think? We could, we certainly could. So, okay, so on Friday we talked about how to represent complex numbers in the complex plane, right? All we have to do if we want to represent a number in the complex plane, remember, is, where's a good example? There was our first vector, right? So like if we want to take the vector 4 plus 3i, then it's going to have a real component of 4, the real part is 4 and the imaginary part is 3. So instead of an xy plane, we have a real imaginary plane, right? So we'd go over +4 along the real axis and up +3 along the imaginary axis. And wherever we end up, with whatever point in the plane has coordinates 4, 3, so it just corresponds to the real part and the imaginary part, that vector represents that impedance, right? Okay? But then we said something else, right? We said that there is this modulus, which is, it sort of looks like an absolute value, doesn't it, right? The modulus, and sometimes people call it the absolute value of a complex number, which is fine, but technically it's the modulus. It's just the distance from the origin in the complex plane, right? So what that ends up being then, if I think about this as a right triangle, it's just going to be, A is the real part and B is the imaginary part. It's just going to be A squared plus B squared equals Z squared, right? Equals the overall, the absolute value of Z, the modulus squared. And so really all we ever have to do then, if we just were to solve that, if I have the equation, the modulus squared equals the real part squared plus the imaginary part squared, square root both sides, right? And so we end up with the modulus is just equal to the square root of A squared plus B squared, just the distance from the origin, right? And that's the overall size of the complex number. Now what happens, just something I didn't mention on Friday, but while we're on this page, what would happen if I had let's take like, let's go back a little bit. Let's take that example. What complex number is being represented there? The coordinates of the point are -4, 0. So what complex number is that? -4. It's got a real part of -4 and an imaginary part of 0, right? So it's the same thing as saying, if I plug those values in, Z is going to equal -4 plus 0i, and 0i is just 0, right? So that's a pure real number. So what if I calculated the modulus of that number? The modulus is just the distance from the origin. Well, how far is that point from the origin? It's just 4, isn't it? Right? If I use my formula, my fancy modulus formula, I'd get Z equals the square root of -4 squared plus 0 squared, but 0 squared is 0, right? So I'm just getting the square root of 16, which is 4. So that's just an absolute value, isn't it? If I take the modulus of a pure real number, you get that it just ends up being a regular old absolute value. Okay? The modulus of -4 is just the absolute value of -4. It's 4. Okay? No biggie. Okay. So then, there's a little review. What do you think, now just think about this, what do you think if we wanted to come up with just a single number to kind of tell us, okay, how hard is it to push current through that circuit? What do you think that number might be? The modulus. Yeah, it's just the modulus. It's the size of that complex number. So if I wanted to come up with the modulus of this complex number, we'll call this one Z1 and we'll call this one Z2. The modulus of Z1 is just what? The square root of what squared plus what squared? 2 squared plus negative 2 squared, so 4 plus 4, just the square root of 8, right? Which we could turn into some decimal. Okay, that's the same thing. I could break that up into square root of 4, which is 2, times the square root of 2. So that's going to be something like 2.83, something like that, if we multiplied that out. Is that right?
Yeah.
Yeah, that's about right. 2.83, something like that. So then, how about over here? If we calculate the modulus of this one, Z2 is going to be the square root of 8 squared plus negative 4 squared. So that's the square root of 64 plus 16, so square root of 80. Whoops, square root of 80. And then what's a perfect square of 80? I guess 4. Oh, 16, right? 16 and 5. So that's going to be 4 radical 5. So that's a bigger number than 2 radical 2, isn't it? Everybody agree? So this one's got more, the impedance is higher. Okay? It's gonna be harder to push current through this circuit than it is through the other one. All right, so that's really simple to deal with when you're talking about series circuits. But what about circuits that aren't in series? What about circuits that are in parallel? Now notice here that I've got this battery, or this is where I plug it into the wall, let's say. I'm plugging it into the wall, and this is where the current's coming through. Well, look, the current can take 2 paths, can't it? It goes around through the circuit, and some of the current's going to go through this loop, where it's going to get pushed through this resistor and this inductor, and some of the current's going to get pushed through the other loop, and then they recombine, right? Everybody see how they would read that? Okay. More complicated then, because how do you know which loop the current is going through, right? It's a more complicated relationship. And so if we want to know what the overall impedance is, here's how we do that. This is, really what it is this. The overall impedance is equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3 for all the circuit elements in the circuit, right? For each loop in the circuit. Each one of those, when I say Z1 and Z2, I'm talking about one of the loops that the current can go through. So I'll have to add up what's the total impedance of that loop compared to that one, right? And if we just limit ourselves, if we limit ourselves to just 2 of those, I could add those fractions up by getting a common denominator. I could multiply this one by Z2 over Z2 and this one by Z1 over Z1. And so another way to write this formula, either way, take your pick. There's one way, or it looks like this. If we want to write it as a single fraction, it just looks like that. If I just combine those fractions with a common denominator, for example. So let's do a little calculation for one of these. So what about for A? So if we look at A then, for part A, we have to figure out, first of all, what's Z1? What's going to be the impedance of that one loop? And that would be just adding things up in series, right? Because we're adding up this resistor and this inductor in series. So what are we going to get? So I'm going to get 3, because that's a resistor, plus 4i. Everybody agree? Because that's a capacitor, or that's an inductor. So we take the impedance times I. What's Z2? Minus 2i. Okay? And so if I want to come up with the total impedance, the overall impedance for the whole circuit, then I've got to use this formula, right? So we get Z equals Z1 times Z2. Well, there's Z1. 3 plus 4i times Z2, which is 6 minus 2i, divided by Z1 plus Z2. Okay, so let's do the math and figure it out. This is good practice using our arithmetic for complex numbers. Well, how did we add complex numbers? That was easy. How did we add complex numbers? George, how did we add complex numbers? What did we do? Okay, so if I've got, now here I've got a real part and an imaginary part, plus a real part and an imaginary part. So yeah, we're just combining like terms. We're just going to add up the real parts, and we're going to add up the imaginary parts, right? And on the bottom of our fraction, what are we going to get? Well, we're just going to get a total of, the total real part's going to be 6, isn't it? 3 plus 6, or sorry, 9. And then 4i plus negative 2i, what's that? 4i plus 2i. Plus 2i, okay, good. So I'm going to get 9 plus 2i on the bottom, right? And then what did I do when I multiplied complex numbers? What was the process there? Okay, I'm going to distribute. All right, so if I distribute the 3, what do I get? I get 18. If I distribute to the other term, I get minus 6i. Now I'm going to distribute to 4i, so 4i times 6 plus 24i, good. And then finally, we got this last one. If I distribute the 4i to the negative 2i, what's that going to give me? Negative 8i squared. But what did we know about I squared? That's negative 1, isn't it? So all that's going to do, because that's negative 1, all it's going to do is change the sign of that term to a positive, isn't it? Right? So then what do we end up getting so far? On the top, we've got 18 plus 8, right? Everybody agree? So on the top, we're getting 26 is our real part, negative 6i plus 24i is plus 18i. And on the bottom, we've got 9 plus 2i. Can we leave it? What's wrong with that number? Yeah, we can't have an I on the bottom, right? We want our answer to look like a complex number in standard form. So when all is said and done, we need to have a real part plus an imaginary part, right? A regular looking complex number. What was our strategy then? What did we do? Okay, good. So we're going to multiply top and bottom by the complex conjugate of the bottom. This is really similar, isn't it, to when we want to get radicals off the bottom, or rationalize a denominator. We just multiply top and bottom by the stranded radical on the bottom, right? That's how we get rid of the square root on the bottom. So it's the same kind of thinking, isn't it? So if we multiply each of these by, what is the complex conjugate of the bottom? Okay, 9 minus 2i. Same complex number, we're just going to swap the sign. If it's a plus, it's a minus, and vice versa, right? So when we multiply across then, on the top, we got to go through that whole process again. We got to distribute and add like terms. So if I distribute the 26 times 9, let's see, that's going to give us 25 times 9 would be 225 plus another 9, so that's 234. Come on, check me. 234. And then if I distribute the 26 to the minus 2i, what's that going to be? 26 times negative 2. There you go, negative 52i. 18 times 9. And we could do that one pretty easily. How are you going to do? Now, I want you to think mental math here. How could I do 18 times 9 pretty easily? Say it again. 9 times 9 times 2, right? 18 is just 9 times 2. Very good. So we could do 9 times 9 is 81 times 2 is what? 162. There you go. So that's going to give us 162i. And then now help me out with this one, please. 18i times negative 2i is going to be what? Negative 36i squared. But what's the I squared do? Okay, it makes it a plus. Good. Now, what about the bottom? The bottom we can do so much faster. right? What is, if I do a product of complex conjugates, do you guys remember what that always works out to be?
It always works out to be the square plus 0, and then the square of the two numbers.
Yeah, I'm gonna go back just a little bit. Remember we talked about this the other day? We said that if we multiply regular conjugates, not complex conjugates, if I multiply just regular conjugates, a plus b times a minus b, I always get a squared minus b squared, right? But if they're complex numbers, a plus bi times a minus bi, what's it gonna do? Well, that last term is gonna be b squared I squared, right? So it's gonna change the sign. So we always end up getting, for our complex conjugates, the product is a squared plus b squared. That's it, okay? So you can do it very quickly and easily. So if we scoot up here then, what's that gonna give us in our case here? What's our a and what's our b? 9 and 2, right? So we should get 9 squared, which is what? 81, plus 2 squared, which is 4. So we're just getting 85 on the bottom. So that's easy, right? The bottom's going to be quick and easy to do. The top one, you got to go through some steps.
Why is it plus 4? Isn't it a squared minus?
No, for complex conjugates, it's a squared plus b squared, because I squared is -1, so it changes that from a minus to a plus, okay? And then now we can simplify this. If we combine like terms, 234 plus 36 is what, 270? So I'm getting 270 over 85 plus, what's the complex part going to be, or the imaginary part? I've got a negative 52i plus 162i, so that's 110i. You agree? Plus 110i divided by 85. And so there's our final answer, but we could probably reduce those, right? I could divide top and bottom by 5 and make things a little simpler. Agreed? So we didn't simplify the fractions, but that's our complex impedance for that parallel circuit. Okay? We good? All right. So last issue then. Actually, that's it for that stuff. Okay. I want to just do a real quick review so I can give you time to work tomorrow. 8 minutes. Okay, that's good. Okay, so here's my question then. We're gonna look at, we're adding some more methods of solving quadratics. What have we got so far? We've got factoring, right? We can solve by factoring in the zero product property, or we can solve by square rooting both sides, by isolating x, okay? And we've done a bunch of practice. We even know how to deal with situations when I square root both sides. If I'm square rooting a negative number, that's all right, because we know how to deal with complex numbers now, right? We still need a little practice, but we're getting there. Okay, so we're going to add 2 more techniques to this. Let's look at this example. Do you notice anything? What are the magic numbers going to be if I try to factor the left side here? What numbers multiply to 9 and add to -6? -3 and -3. So what does this factor into on the left side? And this is on, oh, did I give you guys this handout? Okay, so I'm going to pass this out. You need another handout. You need this guy. Okay, so 1, 2, 3, 5. What's that? Yeah. Yeah, everything on the retake is just on the review. You got it. And then we'll do that tomorrow.
And that we only have tomorrow.
Tomorrow's the only day I'm going to give you in class. Yeah. If you want to do it another day, that's fine, but it's tomorrow's test day. Oh, yeah.
Do we turn this paper?
No, this is notes. Hang on to this. Okay, so here we go. So this is, I want you guys just to see the value of this. So this is a case where it just worked out perfectly. So if I factor the left side, look what happens. We get x minus 3 times x minus 3, or x minus 3 squared equals 20, which makes this a pretty easy one to solve. What are the steps to isolate x then? Because now I can point to a single x. So I'd square root both sides. Good, and I would get x minus 3 equals what? Plus or minus. Plus or minus the square root of 20. And if we make a factor tree for 20, what do we get? 5 times 4, and 4 breaks up into 2 and 2, so I get a couple of 2's and a single 5. So I could simplify that to be 5 radical 2, right? Other way around. 2 radical 5. Couples go out, singles stay in. 2 radical 5, right? Okay, so what's the next step to get x by itself? Add 3. And I'm going to add 3 in front of the plus or minus. And we get the solutions x equals 3 plus or minus 2 radical 5. So I get 2 of them, don't I? I get 1 for the plus and 1 for the minus. Okay. Now what did you notice about the solutions here? Whenever we solve by isolating x, if we use this method, notice that we always end up getting conjugates, don't we? We always get a number plus or minus another number because of the way we do the solution. Interesting. Okay. We'll come back to that later. Okay, so how could we apply that maybe here, that same thinking? What could we do? If we want to use that same technique where I want to be able to solve by isolating x, look, I've got multiple x's here. I've got an x squared and an x, so I can't really solve that by isolating x. That's one we would have to do by factoring if we could, right? But what if we wanted to solve it by isolating x? What could I do? How could I turn this into a perfect square involving x and then maybe some other number? You remember doing this stuff? What does this sound like we're going to be doing? Where we want to coax a perfect square out of this. Completing the square. This is just completing the square, isn't it? So we could solve this by completing the square. Now, what would our steps be? This looks a little different, though, because when we completed the square last time, we were using it to transform a function into vertex form, right? So we set it equal to y, and then we pushed everything to the side with a y on it. Remember doing that, right? Okay, it's been a little while, but you remember doing that. It's on the test, right? So you're going to need to know it. No, actually, it's not on your test, is it? Is it on your test?
I think it should.
Can't remember.
Completing the square is
Yeah.
on some of
It was on, yeah, so was it on the test you guys did for the first test for this semester?
Yeah.
I think it was. I can't remember. Either it was on that one or the one before. I can't even remember.
I think it is. For sure.
One before. I think it was the one before. Right. So anyway, we've done this before. The only difference this time is, phone should be away, please. The only difference this time is instead of having a y on the other side, we're just going to have a number on the other side, right? But it's the same steps. We want to get the left side of the equation, we want to get it in the form x squared plus bx, right? So what's the only thing I have to do? Subtract 56, right? So I'm just going to get, if I move the 56 to the other side, I'm going to get x squared minus 18x equals negative 56. Well, think about the steps we did to complete the square. We're going to add the same number to both sides so that we get a perfect square trinomial that's going to factor into a single factor, so the same magic number twice, a single factor square. And you remember the recipe for that. How do I figure out what the number is I add to both sides? B over 2 squared, half of b squared. So half of b is negative 9. So I'm going to get negative 9 squared is 81, right? That's what I'm adding to both sides, correct? And then what does that do for me? What's my magic number going to be then? Negative 9. It's going to be half of b, so I'm going to get x minus 9 squared equals whatever I get on this side. 81 minus 56 is, what is that, 25?
Yeah.
Okay, so then, now that's easy to solve, right? Get the idea? Okay, we'll come back to that.
What's up, you seem a little mellow.